Hi, everyone. My name's Jimmy Wylie. I'm a malware analyst at Dragos, and I'm here to talk to you about why we thought the industry needed a malware definition and our process, the process that we use to create one. So this is my dog, Velma. This is her usual reaction to me analyzing malware at my office. And she's doing much the same as I sit at my desk trying to figure out what my next task is going to be. Dragos has just released their report on FrostyGoop. It's Modbus TCP malware that was used as part of an attack that disrupted heat to hundreds of apartment buildings in Ukraine. FrostyGoop is the 9th ICS malware and the 5th one the team has reported on since I'd been with Dragos, starting with TRISIS, and then there was Indestroyer, Pipe Dream, Fuxnet, and now FrostyGoop. After an effort like this, we mostly spend our time looking for and answering customer questions. And soon after they started to roll in, my boss messages me on Slack and says, well, folks are asking why FrostyGoop is ICS malware since it uses Modbus TCP. Metasploit uses Modbus TCP. Now, me as a malware analyst, I don't really understand how these two questions are related. Clearly, one is malware and one isn't. And that was only the start. We start to receive more questions, one of which was, how can it be the first Modbus TCP malware? Other research has used Modbus TCP, so obviously that stuff should be the first Modbus TCP malware. Now you can dismiss one question and say like, whatever, that's a one-off. But as many of these have started to roll in, we started to notice this pattern. You know, usually when we release or we report on ICS malware, we don't get questions about why we call these pieces of software ICS malware. And FrostyGoop was the first time people were asking us to like justify it in some way. You know, for instance, TRISIS safety system malware causes multiple site shutdowns at an oil and gas facility in Saudi Arabia. No one is like, why is that ICS, right? Everybody knows, it's obvious. They asked for data on the malware instead. So these questions reminded me more of past situations where we chose not to call something ICS malware, because a lot of times that's when people would ask us, hey, why isn't this ICS malware? So for example, EKANS ransomware. EKANS targeted OT organizations, and it had the ability to terminate Windows processes. Some of these Windows processes had names related to GE licensing software. And because of that ability, folks asked us if it was ICS malware, and we said no. We said that's more of a Windows ability. It's not really an ICS ability. And we said it wasn't ICS specific enough, and you start to hear that terminology. ICS specific, ICS related, ICS themed, and these kinds of things. Or COSMICENERGY, for instance, right? It could speak IEC 104. It was suspected to be part of Russian training exercises, and we didn't call that ICS malware either. And folks asked us about it, but we couldn't find evidence to use it for anything outside of training, much less a real attack. And if we called it ICS malware, we'd have to start calling a lot of researchy looking OT samples ICS malware. And that didn't seem correct to us either. And there were others, things like VPN filter, acid rain, AcidPour, IoT exploit tool, which I'll talk about a little bit more later. When we disclose ICS malware, folks don't usually ask us to justify why. It's when we chose not to call something ICS malware that we would start to get questions. So FrostyGoop represented a bit of an anomaly for us, right? But whether folks are asking us why is something ICS malware or why isn't that ICS malware, the underlying question is always the same. It's like, what is ICS malware? The industry hadn't really defined anything. And at Dragos, we had been applying an informal process based on our innate understanding of the concept. And we'd never put it into words because it didn't seem necessary. And for the longest time, we didn't have enough data to really say anything useful. After we released the report on FrostyGoop, what we realized was that this was a bad idea. And the fact that we didn't have a definition and a shared language for discussing this topic was causing a bunch of confusion. So my boss and I discussed all of this, past ICS malware, the stuff that we had looked at that we discarded or sort of said wasn't part of the category, and tried to figure out what we could do to sort of help with this problem. And we decided to try to define ICS malware in a way that would be easy to communicate. It would be simple to use for assessments, for our Intel analysts to use, and most importantly, it needed to provide a way for us to identify and differentiate ICS malware from those other things that we didn't think were part of the category, the things like EKANS, COSMICENERGY, IoT exploit tool, and the like. And so I start with TRISIS, and I take all the data that we have on TRISIS, the important stuff from the malware analysis and the investigation, the things that if you ask me to just like rattle off, what is TRISIS? These are the things that are going to come to my mind, okay? It speaks tri-station protocol for communicating with the PLC. It can download and upload arbitrary programs. It used a zero-day exploit. The code featured firmware addresses for the system call handler and the network command handler. There was a rootkit installation. I installed a rootkit which gave it privileged access to the firmware. It could read and write arbitrary memory, manipulate the programs at will, any part of the operating system essentially. It featured a key switch bypass which compromised the safety and security of the system. There was only one known deployment that caused multiple site shutdowns at the plant. And we were able to replicate all of this in the lab. Now, from this data, two properties immediately reveal themselves about malware. The first is that there's evidence that's just simple ICS specializations. The way I like to think about it is just when you look at it, you're like, oh yeah, that's ICS stuff, right? These behaviors, these abilities aren't necessarily malicious. They're just sort of ICS actions. Now, this sort of codified ICS knowledge is what SANS refers to as ICS capable. And in that bucket, I sort these three things. The fact that it speaks tri-station protocol, engineering software can speak tri-station protocol. So can malware, it can download and upload programs. It uses a regular protocol for doing that. And the fact that it knew these firmware addresses, right? These firmware addresses represent specific knowledge of these firmware versions, and it's not necessarily something that would only be associated with malware. Engineering software, I would expect a device that downloads programs to this PLC to maybe know certain addresses in the firmware. And so I sort of bucket that into the ICS capable category. And then the next property that reveals itself is just bad consequences, right? These are things that cause harm or negative effects on the OT system or environment. And basically everything else goes into that bucket. The unauthorized privileged access, the key switch bypass, compromising safety, and the site shutdowns. Now, that kind of works, right? These two criteria are a solid start to the process, but they don't answer that question that we were getting about FrostyGoop, right? What about Metasploit and the Modbus TCP modules, right? That thing is ICS capable, and it could potentially have some bad consequences, but we don't call it malware, right? So having just these two criteria of ICS capable and bad consequences for OT can't be enough if it allows for calling red team tools malware. I realize that I'm forgetting about intent. So when Adobe notifies you that there's a new update to Acrobat, you usually install it. But if a stranger hands you a USB in a parking lot and says, this is the latest Acrobat update, you're probably not going to install that update. And the reason is you don't trust that person's intent. And we use intent whenever we assess new malware or suspicious software. So for example, there's a piece of software and it collects your visiting domains, your domain history. Now that could be bad or good, right? If it's collecting those domains to compare it to some kind of safe domain list, you're probably okay with it, maybe, depending on how privacy-oriented you are. But if it's collecting your visited domains as part of some kind of foreign surveillance network, right, you might be upset by it, right? The problem isn't the actual action of collecting domains. It's whether or not that software is intentionally taking this action for a malicious purpose. This idea of intentional design for malicious consequences or malicious intent is what makes malware bad and distinguishes it from your red team tools, offensive software, and other kinds of research. So the difference between ICS malware and something like Metasploit's Modbus module is that ICS malware is intentionally designed for harm against OT environments, whereas Metasploit is designed to help red teamers do their job. I add malicious intent to my list of criteria, and this solves the red team tool problem, and then I resort the data. ICS capable stays the same. The malicious intent stuff doesn't really change anything to do with ICS capable. With bad consequences, though, I'd sort of combine malicious intent and bad consequences in the wrong way, and I need to peel the data apart, separating the evidence into the categories that it most likely supports. So, for instance, a site shutdown could be evidence of malicious design. It could also be evidence of bad design, but it's definitely a bad consequence. So it makes it into the bad consequences bucket, along with the rootkit that gives privileged access, bad read, write, and execute, because it can just arbitrarily write anything into the firmware that's clearly a bad consequence. And the fact that we were able to replicate these abilities in the lab. For malicious intent, I sort some of the other data. So for instance, the fact that it was the only known deployment of this malware was part of an attack. This isn't just some open source stuff that we see laying around or reused all over the place. The rest are code capabilities with no reasonable benign justification, right? These are things that are just bad behaviors, right? And they're clearly bad and there's no excuse for them. So the zero-day exploit, the key switch bypass, clearly compromising the safety of the safety system there. And then this last piece of data that I didn't have in the original list, which is that the rootkit suggests more specific process impacts were intended, right? If they just wanted to shut down that controller, they had the Python code for implementing the tri-station protocol. They could have just sent a regular control command and it would have shut off the device. They didn't need a rootkit, but they put a rootkit there that could arbitrarily execute code, even when that key switch was in run mode. And that suggests to all of us that they were trying to do something even worse. So this whole thing starts to make sense. And I test this criteria against all the other ICS malware we know about. So there's 8 other samples. And it's really easy to look at those samples, find the important data, and they just sort of sort naturally into these buckets. So for example, if we take crash override, is it ICS capable? Well, it speaks multiple ICS protocols, IEC 61850, OPCDA, IEC 104. For malicious intent, there were site-specific IP addresses for the attack, and it could repeatedly turn breakers and switchgear off and on again. Again, a code capability with no reasonable benign justification. And for bad consequences, it disrupted the transmission substation, right? It's very clear bad consequence. So this whole thing starts to look like a process. But there's still some work to do. Bad consequences is a terrible phrase, and it doesn't really accurately capture what I'm talking about. It was just sort of a placeholder, right? So what do we want to do? Well, we want to accurately describe the category of actions that we consider malicious for ICS. Otherwise, folks are naturally going to ask, well, you have this software, it's ICS capable, it's maliciously designed, but for what, right? What can this stuff do? We also want to make sure that we require that the stuff has to work, right? It's not ICS malware if it doesn't have the ability to cause some harm. Otherwise, it's potential malware, broken malware, or intended malware. I don't know, there's all kinds of names you could apply to that. So after a lot of discussion, we land on the ability for adverse effects against OT environments. This property ensures that only working malware gets called ICS malware, meaning there's a burden of proof on the analyst to test the sample or otherwise verify that this stuff works and can actually cause some harm. Basically, to answer the question, what adverse consequences can this ICS software cause? And this would be things like stealing sensitive process information, enabling unauthorized access to OT devices, downloading unauthorized ladder logic, or manipulation of set points, variables, PLC settings, other configurations. So this terminology starts to make sense, but we need to test sort of the exclusions of each of these properties. So we've looked at it and we've said, well, if we have these 3 things, it's probably ICS malware. But what if it only has 2 of these things? What if it only has 1 of these things? What are these things going to look like, right? Does it sort of exclude sensible categories of software? If we look at ICS capable, this just sort of enforces that we stay in the realm of OT and ICS software. This term is going to distinguish ICS malware from regular IT software, the whole sort of category of traditional IT malware, so your things like EKANS and sort of other APT-style implants. While software like that may target OT environments, we're not going to consider them ICS malware unless they actually have some kind of ICS capability. So if we have a piece of software that has malicious intent, has the ability to cause adverse effects, that's probably just regular IT malware that happens to be in an OT environment for whatever reason. Now, malicious intent, we covered this. This is going to exclude our red team tools, our offensive research, right? Tools designed to help defenders may look like malware, but without evidence of malicious intent, we're not going to consider them. And this fits with our previous assessments of things like COSMICENERGY, IoT exploit tool, and some other things that we've looked at. So if something is ICS capable and can also cause adverse effects, it's probably some kind of offensive research, maybe ICS software with the potential for abuse and other kinds of red team tools. And when we look at the ability for adverse effects, like I said, this is just going to exclude broken stuff, things that don't work, potential malware, malware in development. If something is ICS capable and is also maliciously intended in some way, but has no ability to do any harm, I think it's probably broken. Now, for all 3 of these properties, these exclusions start to make sense, seem correct and cover all the edge cases and also exclude samples that we had already previously excluded. using sort of that informal process from before. And we looked at everything. We looked at all the possible variations and combinations to make sure it's, we got reasonable results that made sense to the team. For instance, if something is not ICS capable, it lacks malicious intent, but can have the ability for adverse effects, that's probably some kind of IT software that could potentially be abused in OT. You think about something like PowerShell.exe, that would fit this bill, right? And so software that only has one of these properties or two of these properties, it sort of makes sense when we're sort of looking at this from a malware analysis perspective. So all of this seems legit, and then all that's left now is to take all of these properties, sum it up into a sentence, and we have a definition, right? So that's what we did. And so this is what we landed on. It's a ICS capable software intentionally designed for adverse effects in OT environments. This definition is short, it's sensible, and it accurately reflects how we think about ICS malware. It's also easy to remember, and it provides a simple formula for identifying ICS malware. If a sample has all three of these properties, it's probably ICS malware, and if it doesn't, it's probably something else. And our Intel team has been using this definition since its initial drafts. And I can tell that it seems to be working really well, just how quickly the hunters picked up on this terminology and started to use it to discuss new samples and things that we've been analyzing and maybe discarding and not considering ICS malware. For example, in the fall of 2024, when we were analyzing IOControl, I wasn't part of the initial kind of triage analysis part of this. My coworkers, Kyle and Carolyn, were kind of doing this bit. And I had heard that it had infected like ORPAC fuel devices. And so my initial reaction was like, oh crap, like we're gonna have to spin a team up. We're gonna have to do a public release. There's gonna be all this, what are we gonna do about this? How are we gonna report on it? It's got this new ICS malware, blah, blah, blah. And so I sent him some messages on Slack and we're talking about it. And finally, Kyle just says something like, wait a minute, what are you talking about? Like this stuff isn't ICS capable. It's not ICS malware. Like we're just reporting on it internally like it's any other piece of malware. And I was just like, oh, wait, what? Like I wasn't even expecting them to use this terminology so soon because it was literally fresh out the door. Like I just written and kind of let the team know what I was doing. And so as naturally as they've been using this and we've been using it since, it seems to be working really well. I want to walk you through some other examples just to see how this works. We'll start with FrostyGoop since that was sort of the sample that kicked a lot of this process off for us. Is this stuff ICS capable? Well, it speaks Modbus TCP and it can read and write Modbus TCP registers. So that's a yes. For malicious intent, we had evidence of custom development. We have evidence of them testing the malware on internet exposed encode devices. And we have intel from the security service of Ukraine linking the malware to a known attack. And so that's a yes for malicious intent. And as far as adverse effects, we know that it was linked to a disruptive attack, right, in 2024. So that's a yes to adverse effects. Also we tested it. We tested it on 2 controllers and we tested it against a emulation software and we're able to get the stuff to work. So that's a yes to adverse effects. So we called it ICS malware. Now let's look at some exclusions. So IoT exploit tool is a tool that we found. I don't think there's a public report on this. I think the only public reference to this is in Dragos' year in review report from the past year. This is a tool we found in, I think, 2023. Anyway, we were hunting for ICS-related compiled Python tools. And this thing featured a lot of Chinese strings, one of which we translated, and it's self-identified as IoT device vulnerability scanning, verification, and exploitation toolkit. It featured thousands of exploits for all kinds of devices, IP cameras and the like. But on the ICS side, there were 175 publicly disclosed ICS vulnerabilities with accompanying exploits. It also supports 19 industrial protocols, including Profinet, Ethernet IP, and Modbus, all enough so that it could deliver these exploits. Now, from that description, the ICS capable side and the adverse effects side is pretty obvious. You have 19 industrial protocols. Those are ICS capabilities. As far as adverse effects, you can almost think of it as, well, the adverse effects are the effects that the exploits can cause on the system. So you have things like unauthorized access vulnerabilities, you have denial of service vulnerabilities, and these kinds of things. All of those would be adverse effects for an OT environment. So both of those categories, criteria, get a yes. For malicious intent, though, it was a little bit tougher. The tool includes a bunch of JSON, say, vulnerability information inside of a JSON file, CVSS strings, stored source data, where they got the vulnerability, including links. You can see here we have some one line of output from the JSON file. The tool also featured a bunch of dual use dilemmas, right? These are features for which defensive or offensive applications can be found and justified, right? So the main one is just the ICS vulnerabilities and the exploits, right? That could be used by a red teamer to, test the defenses of a network. It could also be used by a malicious actor, set this up in a server, point it at a network and break in, right? So we weren't really sure which way it was supposed to be used. We couldn't find conclusive evidence in the code either way. Another example of this is the tool could do malware detection. So it featured signatures for certain kinds of malware, Mirai and some other botnets, and some other strains that I can't recall. Now, this kind of antivirus detection seems obviously defensive, but an attacker may actually want to know whether or not another adversary is on a box. And so you could see a justification for this kind of behavior on an offensive side as well. And so we couldn't find conclusive evidence just from the binary itself, whether or not this stuff was malicious. We found persona information and investigated the organization that this person was a part of. And that organization also did defensive and offensive research. And so we couldn't really get a conclusion from the organization that they worked at either. So for malicious intent, we gave it a no. So we have a yes to ICS capability, a no to malicious intent, and a yes to adverse effects. So we concluded this was an ICS red team tool and not ICS malware. Now, the last example I want to talk about is a hypothetical. It's based on a bunch of real cases that we've dealt with that y'all have probably heard of, right? Malware just kind of getting on to your OT network. And a lot of times it's just a file infector virus doing some nonsense. And the reason we're talking about this is it illustrates an auxiliary step when we identify ICS malware. It's that there has to be a link between the ICS capabilities inside of the software and its ability to cause adverse effects in the environment. So we'll pretend we have an IT file infector virus that infects some engineering software and it opens a back door. Now, is that ICS capable? Well, the engineering software is ICS capable, and the virus is inside of the engineering software. So there's ICS capable code laying around, but it really depends on whether or not it's going to use this code. So if we look at a file infector virus, its goal is to get itself launched. And it does this by placing itself somewhere early in the execution history so that when you double click on it, the virus will launch, and then it launches the engineering software. And so you, as the user, think your software launched normally, and you don't know that this virus has just run and opened up a back door. Now, the question becomes, is this virus self-contained and independent of its package, right? Put another way, does it only depend on the package as a disguise to gain execution, or is it trying to use some of this ICS capable code? If the container is only a disguise, then no, it's not really ICS capable because it doesn't do anything. And it would act the same way regardless of whatever software it infects. If this thing infects engineering software, it opens up a back door. If this thing infects Microsoft Word, it opens up a back door. It doesn't care what network it's on. It doesn't do any kind of interaction with the ICS environment in any way that makes you think this might be ICS software, much less ICS malware. But if it's a bespoke Trojanization, meaning they infect the software launches, and it leverages some of the ICS capable code in the engineering software. So now the engineering software is actually a dependency for this virus to accomplish whatever malicious aim. Well, now you can say, yes, there is some kind of ICS capability here, and this stuff would be potentially ICS malware. The reason is because we can find some kind of relationship or code path between the malicious code and the sort of ICS capable parts of the software. So the answer here really is it depends. Now, usually it's no. We haven't encountered some stuff like that. I would argue actually that sort of virus infection is just a whole new piece of malware at that point. If you know another piece of software so well that you can call in to the sort of ICS capable parts, you probably just made new malware without writing the code for the protocol. But either way, the answer has been no so far. Now, I don't have enough time to sort of get into the details here because this case is actually pretty interesting. But the summary here for malicious intent is the way you decide on malicious intent is you need to figure out whether or not it's a purposeful infection of the OT software in order to get into the OT network. Are they targeting a piece of OT software so that they can get into your network and do something? Or is this a file infector virus that indiscriminately targets executables and just so happened to infect some installer because some USB drive was just in the wrong place? Okay, so usually that's been a no, right? We haven't seen any evidence so far of a purposeful infection of OT software to get into an OT network in this way. On the adverse effects side, this is an easy one. A backdoor into your network is bad, right? So in this case, it's a no to ICS malware, even though it can cause some problems. And the verdict here is it's just IT malware. Now, this is how we came up with the definition and tested it, right? We compared all the ICS malware samples that we knew about, and we contrasted it against all these cases that we weren't considering part of the category. And by looking at that, we identified 3 properties of ICS malware: ICS capable, malicious intent, and the ability for adverse effects in OT environments. These became the basis of the definition: ICS capable software intentionally designed for adverse effects against OT environments. This definition gives us a shared language for identifying and talking about ICS malware, and ensures that we're only calling things ICS malware that have been vetted and are real-world threats to the community. These pieces of malware can serve as guideposts, and you can use them when you're designing, tabletop exercises and other kinds of defensive exercises. Now, before we end, I just want to a couple caveats here about this whole discussion. The first is that ICS malware isn't everything. Just because we're talking about ICS malware here and focusing on it doesn't mean that they're the only threats to ICS environments. It doesn't mean that any of those threats are any less serious, and you shouldn't care about something like ransomware, right? Ransomware is clearly a problem, and you need to work on that. I'd argue in a lot of cases, you need to work on the ransomware problem before you work on a lot of ICS malware, right? There's 9 pieces of ICS malware over the course of 14 years, and there's 1 billion+ pieces of other kinds of malware over the course of 40 years. Let's not act like this is the only thing we need to be thinking about. And identification of ICS malware is an intelligence assessment. Now, we don't typically talk about malware analysis this way. I think in the ICS community, we talk about it more than maybe even in the IT community. But it is an intel assessment. And what that means is just because we call something or we decide that something isn't ICS malware today, doesn't mean it's not going to be ICS malware in the future, right? In the face of evidence, potential ICS malware could become real ICS malware if we get more evidence of intent. And the same thing happened with FrostyGoop. We sat on FrostyGoop for a while because it just looked like a Modbus tool. And we weren't sure whether or not this was malware. Then we got the evidence of some of the testing against the ENCO controller. We found some other versions of it. And then we got evidence from the security service linking it. And we were like, oh shit, this is actual ICS malware. We should do something about it. So appreciate you all listening to me talk about this. I know the definitions can be really pedantic and boring, but I hope this helps you establish a good framework and language for talking about this topic. And if you want more details about this, I'm happy to announce that our white paper is out. If you go to dragos.com and you click on resources, there's a resource center. If you click on that, there's a paper. If you look at any of my socials or LinkedIn or whatever, I've posted a link there. You can download that. And this covers a lot of topics. Like what I just did is a very brief introduction to how we think about ICS malware. The paper is going to cover a lot more details that I didn't get a chance to cover. So for instance, it's going to cover how we treat this as an intel assessment. There are formal definitions for all of the properties, including the evidence we use to support each of those properties. And even I think the sources, where we might find that kind of evidence. There's a case study on IOControl, which illustrates how we think about ICS capability, as well as some details on how we talk about the relationship between the ICS capable portion of malware and its relationship to the ability for adverse effects. So yeah, and I think that's it. I think now there's a Q&A or something.